Alright, everybody, welcome back to the fourth installment of Learning Calculus. You can see right here, you have a warm-up, just do it, pause the screen, and then come back to it and recognize that I have the answers here for you. Check them. You can probably use your calculator like on number 6. You probably have it in that point slope form that I encouraged you to use last chapter. As long as you graph that in y1 and your point slope form in y2 or vice versa, if they are coincident lines, then you're good and you have the right answer. If you don't know how to do any of these, shoot me a message on email or come to office hours. Any of those things would be good. So we're gonna get started today on what we call rates of change and tangent lines, section 2.4. So you're probably gonna want to put this in your notes. There's some really kind of weird setups to this particular problem that I have, this activity that I want you guys to do. You're going to be using the function f of x equals x squared, and we'll be finding the slope of the curve at x equals 1. So that's kind of weird. It's the slope of the curve at one particular point. Up until now, we've only ever found the slope at between 2 points. We're finding the slope at a point. So copy and complete the chart below. For each line in the chart, sketch the secant line represented by the points. So some weird stuff there. I'll go through the first line, I'll let you pause, complete the chart, and then you can come back and finish this up. So first thing that we have here is we're talking about the graph of y equals x squared. I think you guys know that it looks roughly like this. At least I hope you do. If you don't, that's what y equals x squared looks like. This first one. We've got x1 is equal to 1, x2 is equal to 5. F of x1, we've got x squared is our f, so we've got 1 squared, which equals 1. F of x2 is going to be 5 squared, or 25. Life hack for you guys, I'm going to point out that all of our x1s, we're keeping that static, so all of our f of x1s are going to remain static as well. Only things that are going to change are x2 and f of x2. Next thing that we want to find is the average rate of change. Average rate of change is just the difference in f of x divided by the difference in x. That's just slope. All we're trying to do is find the slope between two different points. So in this case, we've got f of x2 minus f of x1, 25 minus 1 over x2 minus x1. Over 5 minus 1, 24 fourths, aka 6. The average rate of change on this interval is 6. Now, that second part where it says sketch the secant line represented by these points, the secant line just means connect the point 1, 1 to the point 5, 25. So looking at that, 1, 1 is somewhere around here. 5, 25 is somewhere like way up here. The secant line is the line that connects those two. A secant line is a line that goes between 2 points on a curve. You learned what a secant was in geometry. Of course, your secants in geometry really only reflected circles. Remember in that the circles chapter where you had secants, chords, tangents? That's another important thing that we're going to be talking about. So pause the screen, fill out the rest of this chart. It should take you like 5 to 10 minutes doing the exact same stuff that I did here. Pause it and coming back. Here's the answers. So what you can see, hopefully you noticed that x2 was getting closer and closer to 1. We're kind of like constructing a table of values for evaluating a limit, and therefore f of x2 should be getting closer and closer to whatever f of x1 was. And we see it is. And the average rate of change should be getting closer and closer to the instantaneous rate of change. Now, down here at the bottom, we get an error. That error is produced because we get 0 minus 0, which is 0, divided by 0 minus 0, which is 0. So the slope might exist because we have that indeterminate form of 0 divided by 0. We just have to figure out what thing it is. And to figure that out, well, got a few things, I guess. For each line, we were finding the slope or the average rate of change. I told you guys this right here. The only reason why we have 1 and 1 right here is because we're trying to find the average rate of change, or we're trying to find the average rate of change where x1 is equal to 1. As a gets closer and closer to 1, the slope gets closer and closer to the instantaneous slope. Down here, I have a link to something called GeoGebra to play around with this. And I will tell you right now that I will post, or I am posting this GeoGebra link right in Schoology, so you'll be able to see it. But what it looks like this. And what you can hopefully see on here is we've got the graph of y equals x squared right here, tells you. And we've also got the graph of the secant line between A and B. This happens to be, the only important part on this to look at is the slope. And you can see the slope is 6. This is actually the secant between 1, 1 and 525. And I can draw this B in closer to A. And as I draw it in closer to A, notice that my slope is indeed going down. This physical playing that I'm doing with this is actually drawing B in closer and closer to A, just like we were trying to do on that chart. But what's nice here is I can take B and I can slide it all the way until it is concurrent with A. See how B and A lay right on top of each other? There's the instantaneous rate of change. So this is one tool that I can use to get the instantaneous rate of change, which at this point we can now acknowledge is 2. The thing that kind of stinks about this is this, honestly, it wasn't too difficult to set up, but it was kind of a pain in the butt to draw these points and get this point exactly at 1, 1. And if I had to do this for every single function where I wanted to find an instantaneous rate of change, that would be what we call annoying. So there has to be a different way to do this. So this is called the instantaneous rate of change. Again, the instantaneous rate of change, the slope at a point. We also have another word for this. This line right here is called the tangent line. Just like we had tangents in circles, we have tangents of curves. Tangents intersect a curve at exactly 1 point and represent the instantaneous slope of that curve. I guess a more accurate definition would be a secant, where the 2 points are concurrent with each other. Oh, I don't have a shortcut for that, so I just have to turn it off there. There we go. So you call it instantaneous rate of change, or what we call the tangent slope. All right? So let's go a little bit further. Here, this is just the formula that was on the previous page. It's f of a minus f of 1 over a minus 1. Really, that's a squared minus 1 squared over a minus 1, which is a squared minus 1 over a minus 1. All right? What we want to do is, in that previous activity on GeoGebra, we were trying to take a and move it as close to 1 as possible, but we acknowledge that we can't get it right on top of a. So, if we wanted to find the m inst, that would be equal to the limit as a approaches 1 of a squared minus 1 over a minus 1. And ideally, we would hope that that direct substitution would work, but we've already tried the direct substitution. So we've got 1 squared minus 1, 1 over 1 minus 1. 1 squared minus 1, 0 over 1 minus 1, 0. We get that 0 over 0, which is that indeterminate form. So we have to look for any sort of math that we can do. So direct substitution doesn't work. I keep my limit notation. Ooh, I see a squared minus 1. It is factorable. I can change that into a plus 1 times a minus 1, all over a minus 1. Those are gonzo, and I'm left with the limit as a approach 1 of a plus 1. And now I try my direct substitution. I know it's not going to give me 0 over 0 because I have no fraction here. This is just going to be 1 plus 1, or 2. Isn't that cool? That's really freaking awesome. I now know algebraically that the instantaneous rate of change, or the instantaneous slope, or the tangent slope, is 2. Save that. We're going to come back to it in just a minute. Right now, we have to look at an alternative way of thinking about it. So the alternative way of thinking about it. we could actually think of our average rate of change instead of f of a minus f of 1. Really, we're thinking of it as f of x2 minus f of x1. In every single problem in that chart, x1 ended up being 1, but this is more generic. So we can find it at any point. When we want to find our instantaneous slope, we now don't care that this is x2 and this is x1. Ideally, we want them to be the exact same thing. So we're going to have f of some value, notice I'm leaving that space right there, minus f of that exact same value. So we got f of x minus f of x, that's going to give us 0, over that x with a space minus x. The problem is, we know that we can't have f of x minus f of x, and we can't have x minus x, because we get 0 over 0. So instead of making this first one x, we're going to make it x plus h. And we have to make that first one also x plus h. And we want h. Somebody looked this up a few years ago, asking why we called it h. We call it h because it's a horizontal change. We're changing x just a tiny amount, so it's h approaches nothing. We want h to be 0. Now, in this particular instance, well, okay, not in this particular instance, in every instance, those x's cross out, and we're left with the limit as h approach 0 of f of x plus h minus f of x divided by h. Now, in this particular problem, the problem that we've been doing, we were trying to find out what the slope is at x equals 1. So in the problem that we were doing, we're going to plug in 1 for x. And this is now going to become the limit as h approach 0 of f of 1, not f of 1 plus h. Oh, yeah. F of 1 plus h. I'm not plugging it into the function yet. There we go. F of 1 plus h minus f of 1 over h. In this particular case, our f was x squared. So now we have the limit as h approaches 0 of 1 plus h squared minus 1 squared all over h. And again, I could try to plug in 0 for h. I'm going to get 0 over 0, so I just look for stuff that I can do. I see a binomial being squared, I know how to square a binomial. I see 1 being squared, I know how to square 1. So, limit as h approaches 0 of 1 plus h squared, so we have the first term squared would be 1 plus 2 times 1 times h, so plus 2h plus h squared minus 1 squared gives me 1 all over h. And hopefully some magic's going to happen. Ooh, yeah, 1's cross off. I'm left with limit as h approaches 0 of 2h plus h squared all over h. I can factor out an h on the top. Limit as h approaches 0 of h times the quantity of 2 plus h all over h. H's knock off. I'm left with the limit as h approaches 0 of 2 plus h. Direct substitute. Now I've got 2 plus 0. I guess I'll put that down, even though it hurts me to do it. My instantaneous slope is 2. So one thing to point out here, both of these, this and the previous option, were valid options. We get the same answer. We get 2, we get 2. So those are 2 ways to find the instantaneous slope, or the tangent slope, or the instantaneous rate of change. All of those words are synonymous. Now let's look at this next slide. It's just saying we can use the slope to find an equation of the tangent to the function f of x equals x squared at the point 1, 1. Why are we doing the point 1, 1? Because we knew that we were finding the slope at 1. 1 squared gives me 1, so I know I need to find the equation of the line through that point. Well, we just found out that the instantaneous slope was 2. I happen to remember that formula from last chapter, y equals m times the quantity of x minus x1 plus y1. I plug it in, I got y equals slope 2 times the quantity of x minus x1 is 1 plus 1. There, I've now got the equation of my tangent line. And what's a really fun thing to do, what's super fun, is to pull up your graphing calculator, and on your graphing calculator, to type in, bear with me for a second, there we go. I need this in a place where I can see it. There we are. I go into my y equals, and I can type in x squared, the original function. In the second line, I can type in the equation of the line that I just made, 2 times the quantity of x minus 1 plus 1. And when I graph it, this should be a line tangent to this curve at the point 1, 1. Hoping. Look at that. This perfectly matches the graph that was on GeoGebra right there. So I can see that I've actually constructed the equation of the tangent line, which just makes me feel cool. All right. Yeah, there we go. Why is it twice? Why is it done there twice? Whatever. All right. We can define the slope of a tangent to a curve at any point if we consider the change in the x value, the abscissa, instead of two separate x values. Abscissas, this is found on page 90. This is the slope of a curve that I just gave to you guys. The slope of the curve at point A, comma, f of A is the number m equals limit as h approaches 0 of f of A plus h minus f of A over h, provided the limit exists. It is possible to not have slope at a specific point, but we'll get to that next chapter. I would absolutely recommend writing this equation down without ruining the surprise of next chapter. This is a very important part of calculus. I cannot express how important that formula is. Get it in your notes. I know I'm chuckling, but that is sincerity in my voice. So I'm going to use that formula to find the slope of this curve at this point, at x equals 2. So again, what I'm doing here, m instantaneous is equal to, and I'm just copying this formula directly out of my book, directly off that previous page. I've got the limit as h approaches 0 of f of, I think it's a plus h, but in this case, I know that the value that I'm trying to find it at is 2. Whatever it says at x equals 2, that's your a value right there. So f of 2 plus h minus f of 2 all over h. This problem is going to be a little bit harder than the last one, because this is the reciprocal function. It's just slightly harder to evaluate. Because when I plug it in, I've got the limit as h approaches 0 of 1 over 2 plus h minus 1/2 over h. Just to be clear, I just plugged in 2 plus h, plugged in 2. All right? This scares me because those of you who have had me before know that I hate nested fractions. That fracception is just really frightening to me. So the first thing that I do, I change this. Instead of divide by h, I change this into the limit as h approach 0 of, instead of divide by h, multiply by the reciprocal of h. All right? Times the quantity of 1 over 2 plus h minus 1/2. And now this scares me. I've got two fractions being combined. Shouldn't scare me too much because I happen to know how fractions work. If I want to add two fractions together, I just have to make sure that they have common denominators. And to get common denominators, I use the old standby trick of multiply this one by this denominator over itself, and multiply this one by this denominator over itself. Again, as long as we multiply by the same thing on the top and bottom, we're not changing any quantities, so I'm not doing anything illegal. Again, I have not d-subbed, so I've got limit as h approach 0 of 1 times 2, well, let's keep the 1 over h, times quantity of 1 times 2, so 2 over, I don't feel like distributing that, so it's going to be 2 plus h times 2 minus 1 times 2 plus h is going to be 2 plus h over 2 times 2 plus h. I know that multiplication is commutative, so I'm just going to put it in the same order so that these guys look the same, because now I can clearly see that I have common denominators. I will say one thing that screws people up, this minus, when we get there, we want to make sure that that 2 plus h is in parentheses. So we have the limit as h approach 0 of 1 over h, not doing anything to that 1 over h over there, times the quantity of, see, I've got common denominators, so now I'm just going to put the entire numerator as one numerator, minus the quantity of 2 plus h. If you forget that quantity, you're going to screw up your values in the end. Over 2 plus h times 2. I will caution you now, do not cross off these 2 plus h's because I got a minus here and I got a times e here. That's not possible. However, if I distribute this minus here, and I have the limit as h approach 0 of 1 over h times the quantity of 2 minus h over 2 plus h times 2, I now can cross off these 2's. And now I'm left with the limit as h approaches 0 of 1 over h times the quantity of negative h over quantity 2 plus h times 2. Now I look for stuff that's other stuff that can cross off. Well, I got an h and I got an h. I'm left with limit h approach 0 of 1 times negative gives me negative 1 up top over 2 plus h times 2. Well, I no longer have h's in the top, so I know I'm not going to get 0 over 0. Let's d-sub this bad boy. We get negative 1 over 2 plus 0 times 2. 2 times 2, negative 1 quarter. Wow, that's cool. I happen to know that at the point x equals 2, f of x is equal to 1/2. You know what? I'm going to scale this back a little bit. If my computer doesn't freeze, I hope it doesn't because I don't feel like re-recording this lesson. I'm going to put this in a different color. I'm going to put this in green. At x equals 2, f of x is going to equal 1/2. So the point that I'm going through is 2 comma 1/2. So the equation of the tangent line, because I've got my tangent slope right here, is going to be y equals negative 1 quarter times the quantity of x minus 2 plus 1/2. And why do I do that? I do that so that I can pull up my graphing calculator. There he is, or she. And now I can type into my graphing calculator, if I can find my cursor. There we go. Clear this stuff out. I can put the original function into y1, 1 over x. Remember we were dealing with f of x equals 1 over x. And in x2, I can just type in negative 1 quarter times the quantity of x minus 2 what was it, plus, there we go, plus 1/2. And when I graph it, it should look like I have, look at that. It bumps right into the graph, and I show a tangent line right there. That's really freaking cool. Normal line to a curve is a line perpendicular to the tangent at that point. So I brought up normal like one of the first days of class, but here, in order to find the slope of the normal line at x equals 2, I do need to find the slope of the tangent line at x equals 2. So what we would do here is we would do that instantaneous slope is equal to the limit as h approaches 0 of f of a plus h. Our a in this case is 2. 2 plus h minus f of 2 all over h. I'm going to start applying stuff. At this point, I am not doing, well, it's in calculus, but right now I'm just doing algebra 2 type stuff. So f of 2 plus h would be 9 minus 2 plus h squared minus f of 2 would be 9 minus 2 squared all over h. 9 minus 2 squared, 9 minus 4, 5. 9 minus 5, it looks like I can get limit as h approaches 0 of 4. Again, I'm looking at this right here. 9 minus 4 is 5. 9 minus 5 is going to give me 4 right here. 4 minus 2 plus h squared over h. I see that I can square that binomial again. I'm going to have the limit as h approaching 0 of quattro minus the quantity. It's important not to drop off these parentheses because of this minus right here. 2 squared would give me 4 plus, using my perfect square trinomial, 2 times h times 2, so 2h times 2 would give me 4h plus h squared all over h. Taking it a little bit further, I can distribute my subtraction. Limit h approach 0 of 4 minus 4h minus h squared all over h. 4 and 4 cancel off. I'm left with limit as h approaches 0 of negative 4h minus h squared over h. I personally would factor out the h. You don't have to. There are other ways to do it, but this just lets me see it a little bit better. H times quantity of negative 4 minus h over h. Those h's cancel off. I'm left with the limit as h approach 0 of negative 4 minus h. Plug in, I get negative 4 minus 0. The slope of the tangent line is negative 4. Slope of the normal line, let's just call that m norm, is equal to the slope perpendicular, and the slope perpendicular is just going to be opposite and reciprocal of this. So opposite, positive, reciprocal, 1/4. So I want a slope of 1/4 going through the point of A, 2 comma f of 2. So 2 squared, 9 minus 4 gives me 5, 2, 5. So the equation of the normal line through x equals, or at x equals 2 would be y equals slope of 1/4 for the normal line times the quantity of x minus x1, which is 2, plus y1, which is 5. There's my normal line. And again, just to see it, this one should look like it runs right into the curve and at a right angle with the curve. So let's see here. Y equals, clear that bad boy out. It was 9 minus x squared. Clear that one out. 1/4 times the quantity of x minus 2 plus 5. And fingers crossed, we got it right. Fingers crossed, fingers crossed. Yeah. Right at x equals 2, it goes right in normal to the curve, right at a right angle. Pretty cool. So we did quite a few things today, right? There are some cautions that I do want to give you. Some things that people generally mess up when they're elementary calculus students. Average slope is just the slope. Slope at a point is the limit definition that I gave you guys today. Average velocity is total distance divided by total time. Instantaneous velocity is if you make the function your velocity function, you can have this right here. Velocity is the slope of position if you have position versus time. And here's some practice problems. Take care. I'll see you guys again sometime.